Hello everybody, welcome to our discussion on statistics of rainfall data. This is still a part of our discussion on chapter 2 in hydrology. So chapter 2 talks about precipitation, and for this video we are going to talk about the processes or statistical processes involved in treating our rainfall data. So let us define what is an stochastic process. So a stochastic process evolves in space and time and in a manner that is partly predictable or deterministic and partly random. So hydrologic processes are stochastic processes. That is why we need the concept of probability, statistics and probability to deal with the rainfall data. So in this chapter or in this part of our lesson, we're going to talk about these stochastic processes. All right, but before we go to that one, let us recall some basic principles in probability and statistics. So for the first part, let us talk about probabilistic treatment of rainfall data. Let us recall, a random variable is a numerical measure of the outcome of a probability experiment. So its value is determined by chance. Random variables are typically denoted using capital letters such as X. So in this case, our random variable are our measurement of rainfall. Okay? And then we talk about probability distribution. Probability distribution provides the possible values of a random variable and their corresponding probabilities. Recall in your statistics that a probability distribution can be in the form of a discrete probability distribution or a continuous probability distribution. So most often than not, in hydrology, we are going to use the continuous probability distribution. All right? So a population is the entire group or data to be studied, while the sample is the set of observation x1 until xn taken from the population. Okay, you know this from your statistics, and it is assumed that samples are drawn from a hypothetical infinite population possessing constant statistical properties, while the properties of a sample may vary from one sample to another. All right, so in the case of rainfall data, it is agreed upon that those that are measured in the field, these are sample. Okay, these are sample data. While it is hypothetically assumed that there are infinite number of rainfall data. Okay, so we are going to treat yung mga recorded measurement natin from the field as sample observations. All right. And then we have sample space. Sample space is the set of all possible samples that could be drawn from the population, while the event is a subset of the sample space. Okay? Sample space, ito yung pwedeng mangyari. Okay? I mean, lahat na pwedeng mangyari from the population, while the event is just a subset of the sample space. Okay? So, parte lang siya ng sample space. Alright, so let us talk about probability. Probability of an event. The probability of an event is the chance that an event will occur when an observation of the random variable is made. Okay, so a probability of an event A has a symbol P of A. So we have a symbol PA. That we read this as the probability of event A is equal to N sub A all over N. N sub A is the number of observations or the number of events. I mean, the number of possible scenarios for the event. Okay? Itong N naman dito sa baba is the sample space. Okay? So, the probability of any event A, P sub A, P of A, must be greater than or equal to 0 and less than or equal to 1. So, that is the probability of A must be greater than or equal to 0 or less than or equal to 1. Okay, you know this already from your statistics class, that the probability can only be between 0 and 1 inclusive. Okay, so let us talk about the principles of probability. The total probability, the sum of all probabilities of sample space, is completely divided into m non-overlapping events, a1, a2 until am. Okay, the total should be equal to 1. Alright, so the total probability of any non-overlapping in statistics, we call this mutually exclusive events. Okay, so if we have mutually exclusive events and we add their probabilities, the sum should be equal to 1. Okay, we also have the principle of complement. So if we have an event A, the complement of A has a symbol of A and with the bar above. Other symbols for complement is A apostrophe. Okay, you may see this from other books. Okay, this is another symbol for complement, but for our discussion here, we are going to use a bar, okay, for the complement of event A. So the probability of event A is just equal to 1 minus the probability of event A. So basically, the sum of A and its complement should be equal to 1. Okay, so the sum of an event, the probability of an event, plus the probability of its complement should be equal to 1. We also have conditional probability. So the notation for conditional probability is this one. This is read as the probability of event B given that event A has already occurred. Okay, this is the probability that event B occurs given that the event A has already occurred. Ibig sabihin nito, kapag nangyari na yung A, what is the probability that event B will happen? Okay, that's conditional probability. But when event A is independent of event B, ibig sabihin, walang kinalaman yung event A kay event B, then they are called independent events. Ang mangyayari niyan, the probability of B given A is just equal to the probability of B. Ibig sabihin, hindi apektado kahit given man si A o hindi, the probabilities of B is still the same. So that's the principle for conditional probability. This is what I'm talking about here. So kapag independent yung A and B, the probability of B given A is just equal to the probability of B because event A does not affect the probability of event B. Okay, and the probability of the intersection of A and B is just equal to the product of the probability of A and the probability of B. So basically, we just multiply the probability of the two events if we want to know their this is other term for end, diba? The intersection, the probability of A and B. All right, A and B both happening together. All right, if we want to know their probabilities and if they are independent, we just need to multiply their probabilities together. Okay, so that are the principles of probability. Let us take a look at some of our examples. So we have here the values of annual precipitation in College Station, Texas from 1911 to 1979 shown in the table, and the one on the right is a plot, what we call this a time series because the x-axis is in year and of course the y-axis is the precipitation in inches. The question is, what is the probability that the annual precipitation R in any year will be less than 35 inches, greater than 45 inches, or between 35 and 45 inches? So basically, the figure on the table, the numbers on the table is the annual precipitation in College Station. It's measured in inches, okay? Annual, that means the total measured observation for 1 year. Okay, so 1910 plus 1, that's 1911. So we start from 1911 and we end up at 1979. Okay, that's 1911 to 1979. If you take a look at this one, we have N Okay, let us write n is equal to, that's 79 minus 11 is plus 1, that's 69. So we have 69 total number of observations. So n is equal to 69. Alright, let us take a look at the first example. What is the probability that the annual precipitation are in any year will be less than 35 inches? Okay, so for letter A, the probability that the annual precipitation R is less than 35 inches. Okay, so we are looking for the probability that R is less than 35 inches. So basically, to solve for this one, let us count the number of observations that are less than 35 inches. So let us count. Okay, if you try to count, first one, we have 31. Less than 35, so you can take a look at the figure or the table and check all that are less than 35. Okay, so we have this one is less than 35 as well. This one 27, 26, 25, 23, 29, 35. So these are also counted, right? Okay, these are also counted right there, and then there. Okay, let's count. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay, so let us try to look at if there are some more. That's 22. Let us see. Let us double check if there are values less than 35 that we have not counted. This one is also less than 35. So that's 23 in total. Therefore, this is equal to 23 out of 69. So you can round this off to 3 decimal places if you want that. Okay, so 23 over 69, the 3 decimal places is 0.333. Okay, 0.333. Okay, this one, R is less than 35 inches. We can actually write this to whatever capital letter you want, as long as you define what is that. For example, we can define A is the event that R is less than 35 inches. So we can write this as P of A is equal to 23 over 69, or that is 0.333. Okay, whatever, as long as you arrive at the correct answer, your answer should be correct. Okay, for letter B, using the same technique, we are going to solve for the probability greater than 45 inches. So let us take a look at the values that are greater than 45 inches. So you do that, and we come up with, we should come up with 19. Okay, so there are 19 values that are greater than 45. So we have 19 over 69. Okay, for 19 over 69. So if we denote B as the rainfall greater than 45 inches, we can say that the probability of B is equal to 19 over 69. So if we divide this and round this to 3 decimal places, 19 over 69 is 0.275. Okay, 0.275. That's the probability of obtaining a rainfall greater than 45 inches. And finally, for letter C, we are looking for the rainfall between 35 inches and 45 inches. So if we denote the event C for rainfall between 35 and 45 inches, so we have the probability of C is equal to, basically we know those that are less than 35, so should be equal sign there including 35 and 45. So if we count, there are 69 number of observations. If we less 23 less 19, we should come up with what is that? How many is that? So that's 69 minus 45. Sorry, 69 minus 23 and then minus 19. We should come up with 27 over 69, which is equal to 0.391. Okay, so 0.391, or near that. Okay, and then if we, since these three are complements of each other, di ba? The sum of these three should be equal to, or should be near 1. I may not be equal to 1, but can be near 1, like 0.999, 0.998, something like that. Okay, the total probability, total probability is equal to, if we add them together, 0.333 plus 0.275 plus 0.391. The sum should be approximately equal to 1. Okay, may not be necessarily equal to 1, can be 0.999 or something like that, because we have rounding errors in this case. All right. Okay, so that's it for our example on probability. Let's take another example. Assuming that annual precipitation in College Station is an independent process, take note of the word independent there. Calculate the probability that there will be 2 consecutive years of precipitation less than 35 inches. Compare this estimated probability with the relative frequency of this event in the dataset from 1911 to 1979. Okay, so 2 successive years of precipitation less than 35. Okay, from our previous example, the probability that the rainfall is less than 35 inches is equal to, if we take a look at our solution in our first example, we have 0.333. Okay, that's the probability that the rainfall is less than 35 inches. So we have 0.333. Now, if we are looking for the probability for 2 successive years or consecutive years, then the probability that we have less than 35 inches is using our principle of probability, given that the 2 events are independent events, we just need to multiply the probability of getting rainfall less than 35 for the first year and another probability of rainfall less than 35 for the second year. So basically, the probability, if we take a look at, since we have already used C, if we say that event D is the 2 successive years, 2 successive years of precipitation less than 35, then the probability of D is just equal to 0.333 multiplied by another 0.333. Or basically, we can write this as 0.333 squared. Okay, so since the process is independent, we can multiply that one, 0.333 multiplied by another 0.33. And if we multiply, we come up with 0.111. So this is the probability that 2 consecutive years will have a precipitation less than 35 inches, 0.11. Now let us compare. If we take a look at the figure or the table on the left, how many consecutive years of precipitation less than 35 do we have? Okay, so let us take a look at the data, and let us look for 2 consecutive years with less than 35. Let us go back to our original data here. Okay, this is consecutive, right? This is another consecutive year, so we have 1 and then 2. We have another here, 3, and then we have here 4, 5, 6, 7, 8, and then 9. So we have 9 times that we have 2 consecutive years which precipitation is less than 35 inches. So if we do that and compute for the probability, let us compare. So the probability of D based from the table, from the given data, is just equal to 9 over 69. And 9 over 69 is equal to not 69 anymore, because we only have 68 pairs. All right, we only have 68 pairs. We have 69 individuals, but we only have 68 pairs. So 9 over 68 should be equal to 9 divided by 68 should be equal to 0.132. And this is not really far away from 0.111. Okay, so this is our theoretical probability. Okay, so this is our theoretical, and this is our empirical probability. Okay, so we have 2 different answers. This one is from theory, from the formula, and this one is from direct observation from the data. Okay, so that's how we use the probability in discrete events. All right, so